Sí, bueno, muy buenas tardes, buenos días, depende de donde estemos en América Latina o en Europa en este caso particular. Bonjour Clément, él está en Nantes,
Bonjour.
en Francia. Y bueno, el seminario va a ser en inglés, podría ser en francés, pero no creo que haya tanto público, ¿no? Eh, Así que vamos a pasar al inglés. So, this is a special occasion. We are going to run this seminar in English because we have a distinguished guest, Clément Albinet, who is an engineer from École Centrale de Nantes in France. And he also got his Master of Science degree from the University of Nantes. And since 2015, he is with the European Space Agency, the ESA, Sensor Performance Division, Products and Algorithm Section, to work on the BIOMASS mission. He is currently the data quality manager of the BIOMASS mission. So the seminar will report on the status of the mission, the data acquisition strategy, and the BIOMASS product family. Each BIOMASS product performances will be shown, as well as the information on how to access and use the mission products. So we're looking forward to that. We're eager to use the data. Thank you very much for joining us. Clément, merci beaucoup. Alors, tu as 45 minutes et après, il y a des questions. Bienvenue.
Perfect. Thank you very much for your introduction. I will share my screen right now. Okay, can you please confirm me that you can see properly the slides?
Perfect. Everything works
Okay.
fine.
Perfect. I apologize, but in the middle of the presentation, I will have to leave for a few minutes. So I will just turn off the camera, keep talking, keep presenting, and get the computer with me, but there might be some background noise. So I'm Clément Albinet from ESA, located at Essuin, which is the center of ESA in Italy, close to Rome. And I'm the data quality manager for SAR missions, in particular for the biomass mission. So first, as a kind of introduction, why are the forests important? You have this proverb from South American natives that say that the trees are the column of the world, that when all the trees will be cut, the sky will fall above us. If you read Asterix, you know that the French were scared to have the sky falling on their head. In a more concrete way, I mean, we can say that forests have always played an important role in human history. But for us, in the short term, it's more the fate of CO2 emissions. Here, if we see the different sources and sink of CO2 emissions, we can see that we have the highest uncertainties. I don't know if you can see my cursor on the bottom left here and on the middle right. The highest uncertainties are related to the forest because we have tools that are measuring precisely the CO2 in the atmosphere. The ocean are quite known. The emission coming from industry can be very well measured because we have price, we have taxes, we know the kilogram of fuel which is burned. But the tree cut and the growth of the forest are something which is not very well known. And these uncertainties, when we put them in the carbon model, we realize that they lead to very, very different estimation in the future of impact on the climate. Here you can see different models of carbon fluxes over the year. And if we estimate them in the longer term in the future, we can see that these models are very different outputs. And this is coming because our knowledge on the carbon fluxes has too high uncertainties when it relates it to forests. So a key component of the forest that we would like to measure, a key component of the carbon cycle, is what we call the biomass. And why that? Because biomass is half made of carbon. And the forest holds between 70 to 90% of the Earth's above ground biomass. And the majority of the forest biomass is located within the tropics. What do we call biomass? It's the dry weight of woody matter and leaves in ton per hectare. So we take all the trees, we let them dry, or we just remove the water, and we weight them, and this is what we call the biomass. It's not only for the biomass that it's quite important to measure and to know that, because the forests are very important in terms of services for the human. 1.6 billion of people are relying on forest for their subsistence. 3/4 of accessible fresh water are from the forest watersheds. They provide a major source of energy for about 2.6 billion of people, with the wood always been very important for industry, source of energy. And it's a major life reservation. 31% of the land surface contains more than 2/3 of terrestrial life species, plants and animals. And today, with the current satellites, we're able to derive some biomass maps. Here you can see the three most well-known, coming from NASA JPL on the top right, or in the bottom coming from JRC, the Joint Research Center from the European Commission. And what you can see very fast is that these results are very different. This is coming from the fact that the satellites that we have currently are not adapted to measure the content inside the forest. They're usually based on high frequency electromagnetic wave system sensors or optical sensors that just see the top of the forest. And we don't know what is inside the forest, what is going up to the ground of the forest. So we have very high uncertainties when we create maps. How to measure the weight of a tree? We could, as I was explaining before, we could cut the tree, we could let it dry, and we could weight it, but we don't want to cut a large amount of forest of trees, because the idea here is to measure it to prevent cutting forest. So what we usually do is that we cut a few trees, we measure, let's say, the biomass of these different species. When we know the density of the wood, because every tree species have a different density, we're able to derive some odometry functions, let's say, that allow to estimate the above ground biomass without cutting the tree, by just estimating the height with a laser system and measuring the diameter of the trunk. This is not that easy when you deal with tropical forests, because some trees, as you can see here, are very, very large base. Measuring the diameter of a tree is becoming something extremely difficult. So we need systems that are able to measure the biomass at a larger scale much faster in areas that are difficult to go. So we need to estimate the forest biomass, and we call it AGB, above ground biomass, the forest height, and the forest disturbance. When we cut the forest, we know, linking the AGB and the disturbance, the area cut, how much biomass was lost, so how much carbon was released. This information, which is needed, is crucial in the tropics. The measurements are needed where the changes occur, and the effective scale of the change, which is the hectare scale. Measurements needs to be wall-to-wall and repeated measurements over multiple years to be able to measure deforestation and regrowth. Regrowth is quite slow. And in terms of precision, the biomass accuracy needs to be around 20%, and 20% at the hectare scale, which is comparable to ground-based observations. So the solution to that is the biomass mission that we proposed. It's what we call the 7Earth Explorer mission. It was deployed, launched in April 29th. I don't know why the video is not working. I apologize for that. It's what we call an interferometric polarimetric P-band SAR, and it's designed to observe the forest height and biomass. So what is the Earth Explorer? At ESA, we have three families of mission. Here you can see all the mission we have currently and the one we are preparing. We have a column for meteorological missions that are built by ESA and that are operated by EUMETSAT. Operational missions we call the Copernicus family. Maybe you've heard about Sentinel-1, Sentinel-2. Sentinel-1 is the SAR mission, Sentinel-2, the optical mission, and then some science mission that we call the Earth Explorer, that are innovative mission, an instrument that we build for the first time and we launch them in space. And BIOMASS is one of its kind. Why do we need the P-band SAR, the P-band frequency band to measure the forest biomass? Because biomass mission will be the first SAR at P-band in space, is the first SAR at P-band in space, because it's a very, very low frequency that don't stop only at the top of the canopy, but really penetrates in the canopy up to the ground. It interacts with the woody element of the vegetation, the one that contains the biomass. And the forest state can be estimated with one satellite. So concrete point of view, the satellites see the trunks and the big branches. And it's the lowest, the lowest frequency, the longest wavelength, which we can operate from space, because the different frequencies are limited by laws to be open, and lower frequency would bounce on the ionosphere. So it's really physically the lowest frequency we can operate. Here you can see what the different frequencies see. So X band, which is what TerraSAR, Cosmos SkyMed, ISI can see. So really the needles, the few centimeters, few centimeters. Then at L band, you see 10, 15 meters. So small branches, trunk, big branches, which is good for temperate forests, but tropical forests are taller than 10, 15 meters. So there's a saturation. And at P-band, we see the trunk and the big branches. And the big branches and the trunk are something quite stable in time, more than needles or small branches. So they stay what we call coherent. So it means with one satellite, if we fly few days later, the scene didn't change that much, and we can use multi-pass techniques, which is quite important. This is what you can see here when we compute the coherence. So if we make acquisition, with different times, we can see that at C-band, which is like Sentinel-1, already after 1 day, we lose all the coherence. So the techniques that we can use for multipass techniques, they need to be on top of 0.7. So it's not possible at C-band. At L-band, it could work a little bit, but there's a degradation after a few days. And at P-band, we see that we stay stable over 20 days, more than 20 days. So with one satellite, we can do repeat pass interferometry, for example, quite easily. Here you see some parameters for the satellites. We'll not go through all of them. You find them on the website in the literature. It's for information. There are 3 swaths. It's quite a simple type of operation. You see swath 1, the swath 2, swath 3. It's strip map only operation. So there's no fancy acquisition mode. It flies at 6 in the morning, ascending, 6 in the evening, descending. And there's a swath, which is quite small, between 45 to 55 kilometers. To give you an idea of how to interpret this number, because there are more engineer and DB's number. So the satellite is sending 100 watts in terms of power radar pulse. It's sending this pulse. They are 30 microseconds long, and they are sent like 3,000 times per second. And they are sent like 3,000 times per second. And they are traveling to the forest, coming back to the satellite, and they are measured with, let's say, an intensity of 0.0000001. They are 13 zero digits behind the comma. So it's extremely, extremely precise. It's a very, 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 very low signal. And it's, of course, impacted by a lot of elements, which is the ionosphere. So the fact that the atmosphere is electrically charged, the rain, the forest type, the topography. So it's impacted by a lot of elements. To build that type of satellites, it costs a lot of money. It's complicated. It took almost 20 years from the first proposal, 9 years to develop, build, and test a satellite. And the total budget is €500 million. So covering pre-development, launch, operation, and the cost of people. More than 80 companies were involved from 23 countries, around mainly in Europe, but also Canada, USA, and Australia. and more than 700 people were involved at the peak of the development time. And you can see here on the right some elements. You have a reflector on the bottom right, which is 12-meter diameter to be deployed. It's super large, and it could only be deployed in space or in particular facility because it could not sustain its own weight. It's the first time we have that type of satellite in space. But to calibrate the satellite, we needed also some calibrator. So we had to build a unique calibrator only for this satellite that you can see here. Only this calibrator costs like more than 10 million euros. On the bottom left, you see an antenna, which is very large, 5-meter diameter antenna. It's a very low frequency we have for biomass, so it was extremely challenging. On the bottom middle, you can see that the hill was leveraged, forest was cut just to put this calibrator. And the calibrator even needs another calibrator to be calibrated, as you see on the bottom right. So it's a unique piece of engineering that is located currently in Australia, in New Norcia. Here, I hope you can see the video. Please tell me if you cannot see it. But you can see the satellite before the launch. So it was early first trimester. It was integrated in the fairing of the rockets. It was brought to French Guiana. So we are launching our satellites and rockets from South America. Here was put on top of a Vega rocket, which is the smallest rocket we have, but it's already 35 meters high and 210 tons. So it's something quite large, as you can see. It was all integrated. And then it was launched successfully on the 29th of April. I will add a few seconds of video just to show that. So the orbit was very good. Everything was very fine. We went through 6 months of commissioning, and then we started releasing the data. So in terms of coverage, I was explaining before that we have only one satellite, but we need to fly over the same area several times to be able to use interferometric techniques. And the problem is that we have only 50 kilometers of swath. So it's very small. So we cannot do like other satellites that fly regularly all over the place. We have some particular type of acquisition. So we send pulses, we receive pulses, we fly over an area, we go all over the world, and we fly several times over the same area. In nominal phase, we fly 3 times over the same area, and we're having the satellite drifting. So we see the same area 3 times, but from slightly different observation angles. And then when we flew over the globe 3 times, over the same swath, that we call the swath 1, we steer a little bit, we roll a little bit the satellite, make it turn a little bit, and we start acquiring a next swath. We do that 3 times again, and then we roll the satellite a little bit again, and we acquire again swath 3. 1, 2, 3 times. And once we finished the cycle, we have a repositioning maneuver where the satellite will go on the highest orbit for a few hours, a few days, and then we'll go back to the next orbit and we start again. To illustrate it a little bit differently, you saw on the video the 3 acquisition in green, 3 acquisition in pink, 3 acquisition in blue here. So you see on the bottom, you have the across track distance with a swath of almost 50 kilometers. You have an overlap, of course, and you need time. You have 3 days between 2 consecutive passes. So you have 1 pass in green, 3 days, second pass in green, 3 days, third pass in green, 3 days, then pink, 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 blue, 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 repositioning maneuver. We start again, repositioning maneuver, etc., etc., etc. And it takes a lot of time to cover the globe. So in this end phase, nominal phase that I presented, we need 7 months to cover the globe. So you have consecutive passes with 3 days in between, and then you have no acquisition during 7 months. Here you can see IOC for in-orbit commissioning. So it's the commissioning phase where we're having exotic configuration. This was to qualify completely the instrument, the antenna pattern, test the processor, test the instrument, read its exotic configuration. And since the 21st of November, we are in the TOM phase, tomographic phase, which is following the same approach that I was showing before, except that instead of having 3 passes, we have 7. So we need 16 months to cover the globe. We don't cover completely all the globe. We have systematic attributions for forested areas that you can see in red here. We have best effort for secondary objective that are in yellow, so it's deserts, a little bit of ocean, Antarctica. And you can see that in gray on the top left, so North America and Europe, we cannot acquire because of the US Space Object Tracking Radar, which is the military radar protecting the US against nuclear missiles, to summarize. And the problem of the P-band that we're using is that there's a priority for military use. So we cannot operate in this band if there is a military application. But there is no tropical forest over this area, so it's not dramatic. There will be 3 products that will be measured and provided, biophysical products. As I was saying before, the above ground biomass, 200-meter resolution, forest 8, also 200-meter resolution, and disturbances at 50-meter resolution. How to derive, to retrieve these parameters? We have 3 techniques. The first one is to just use the backscatter. So we send a pulse, we receive a pulse. We just check the intensity of the signal. And this is from that we can make a linear modes. And with one pass, we can derive a biomass map. But we can also use some interferometric techniques. I will detail them a little bit later on. So we fly over the same area, seeing the same area from another observation angle, like 2 eyes, that will allow to see in 3 dimensions in a certain way. And here we have an information about the canopy, let's say constitution, because we have a penetration, we have a center of phase that will be located within the canopy. But what we can do is that fly even more with different observation angle, which is in this tomo phase, to do tomography with 7 passes. And here the idea is to reconstruct in 3 dimensions the forest. It's the first time we have a space mission really made to do that from space. So as I was saying before, the 3 techniques, the first one, here you can see an example with airborne campaign data, where we just link the backscatter with the above ground biomass. So you can see this linear function that works. You can see here the problem that according to the type of forest, tropical at the bottom or temperate at the top, the trends are not the same. So you need different models according to the type of forest that you're observing. Then, as I was saying before, you can use an interferometric technique, the most famous, we call it Pauling SAR, for polarimetric interferometric SAR. The idea is that from 2 different observation angles, you can retrieve a center of phase. These techniques was used, for example, with higher frequency. The center of phase would be located on top of the element, so on top of the ground, on top of the forest. And this was used, for example, by SRTM, the shuttle mission, to make a topography. This is typically the techniques to derive topography at higher frequency. Here we have a low frequency, so the center of phase is located in the middle of the forest. But we have also a polarimetric measurement. We are measuring only at full pole, so we are able to measure different polarization. And the forest is not an isotropic medium. By that, I mean that the trunks are vertical, the branches are at 45 degrees oriented in different ways. So the trunk are not in all the directions. So different polarization will have center of phase located at different elevations. Using a model and the fact that these different elevations are different height, a model of attenuation, you are able to retrieve the forest state and then the above-ground biomass. The third approach is to use different type of acquisition. Here it was with Urban Campaign from different angles and to make a kind of 3-dimension SAR that we call it tomography. It's also done in the medical world. So here you see vertical cuts of the forest at different polarization, where you can see that the HV polarization is more sensitive to the cover and the HH polarization more sensitive to the ground. And here you see horizontal cut where you can retrieve like a flux tower in the middle of the forest. It's in metal, so you can see it very well. In terms of product that we'll provide, so you can see here row level 0 will only be level 0 focal value users. So in case people want to have some access, we can provide access to that, but there's no big benefit for scientific community. Then we provide the usual level 1 product, or SAR products. I will go more in detail later on. Some start of biophysical retrieval here that we call level 2A that are following the frames of acquisition. And then what we call level 2B and level 3 that would be, let's say, consolidated level 2B that are tile-based. So following different tiles like the Copernicus dam, for example, which is cut by tiles. And you have some documentation and access to the source code of the processor within this, what we call BioPal. I will go again to that later on because it's something quite innovative. You have a QR code that you can take as a picture. I will show it again later on and I will share my slides so you can access them afterward. But if you're in a hurry, you can take a picture right now. So in the product family, we have level 1. This is standard level 1. If you work with Sentinel, work with that instant range geometry, which is this observation in SAR. Level 1B that corresponding to the same as level 1B that you have on Sentinel-1, which is multi-looked, so the pixels are squared, but still in the central geometry. And level 1C are level 1A that are stacked together. So if you're familiar with SAR, if you do interferometry, we stack them for you, we correct them for you, we adjust them for you. They are very well calibrated, they're ready to be used for interferometry or tomography. So this is the one to start if you want to use that type of techniques. So it's exactly the same resolution at level 1A, but they are grouped together. It's the cut-in frame of 21 seconds, knowing that the level 0 are a little bit longer, but we cut them in different pieces with an overlap. And in terms of file format, we improved a little bit the file format using all the different standards. So annotation, which is all the metadata to be used, additional information. You have stack metadata, and the measurements are cloud optimized GeoTIFF. So you can get only the measurement if you see a module, phase. You can get a quick look only, so you can get only part of the information. You don't need to download completely everything. I apologize, but I will end. Okay, I'm back. I apologize. So what we have, which is quite interesting, is that we have a modern access that allows to get access to the individual files of the product without the need to download all the product. Currently with standard mission, you need to download the whole product, even if you use only, I don't know, one polarization, or only if you want to get one element. Here you can really just download one part of the file, all the quick look, for example, for one pass, or just query the metadata to be sure that the rest of the file is interesting for you before downloading everything. Here you can see ascending, descending for level 1C. You see that they overlap quite well. So level 1C, as I was saying before, they are stacked. So it's exactly the same structure as the level 1A SLCs, except that we add additional metadata to indicate what was the master, which correction were made, and information on the result and quality of the correction. The level 2A are the preparation for the biophysical products. So they are tile-based. we have a forest state, which is a real forest state, forest disturbance, which is a real forest disturbance. But ground notch is not an AGB. It's a backscatter without the contribution of the ground. So we use the interferometry, the different observation angle, to remove the contribution of the ground. So it's kind of intermediate product. And the idea is that for a cycle, so for the first 16 months, and then later on for every 9 months, we put together all the ascending, descending of the level 2A together to derive the level 2B. And the level 2B then are tile-based. So you can see here 200-meter resolution for the forest state and GBD, which is there an AGB. Here is a real biomass measurement, and 50 meter for the forest disturbance. We have interesting tools and data access, a little bit more modern. Here, if you are interested, you can see on the left, you can have access to the website to download the data. If you already connected and downloaded data for biomass for another mission, it's the same login and password. You don't need a new login and password for that. It's a standard thing. And on the right, we have this platform that helps you to process data. I will go more in detail later on. You can take a picture of the QR code and look for them on Google. Here you can see the interface to query data, to get data. What is interesting is that in the catalog, we have 291 UC collection. So all our Earth Explorer is located there. So it's not only for the biomass data. Everything is there. And if you look for biomass, you can see all the different collections. Some are restricted because they're under development. You can go all around the globe. You can search by date. You can search by a different by different parameter, and you can see by area. You can get the footprint of the data you want. You can add them to the cart, and you can download them. Okay, and we have a three very innovative thing in this mission. The first one is this concept of mission, algorithm, and analysis platform. So I was talking about that before. It's a virtual, open, and collaborative environment, which allows to enable researchers to discover, process, visualize, analyze large volume of data, provide tools and infrastructure to bring data in the same coordinate, to enable comparison, analysis, data evaluation, data generation. And it's a science control environment, development. So you can develop, modify code, generate data. And it's protecting you, keeping your intellectual property. Contrary to Google Earth Engine, where you lose intellectual property for whatever you put there. It's free and open, you can access it. Second innovative point is for the first time ever, we have open source processor. Today, we still have some level 1 parts that are closed, but the idea is to have everything open in the future. But all the code that are made to generate the ESA mission data are completely open. Anybody can see the source code and process the data, and you can get them there. You can take a picture if you want of the QR code, and you can even contribute to it. If you have a good idea, better idea than us, you can make some pull requests. And thirdly is the validation data, the in situ data, which we use for validating the data. Usually the type of data is not open. And for the first time, we'll have the data that will be open. It's called GeoTrees. It's a big network of data. It's made not only to support the biomass mission, but also JEDI and ISAR mainly, but any also space mission working on forest, let's say. It's a network contribution from different agencies, different funding of sites with GLS, ALS, field measurements, ancillary information, etc., etc., etc. So it's quite large. It's quite detailed. I apologize again for Okay. An interesting thing is this concept of disk. So it's the team, the disk we have to work on the data quality of the mission, improving data quality of the mission. So they are part of the ground segment. They ensure that the low-level science data are transformed into calibrated and validated user products so that the products are the best as possible and that you can trust them. I mean, you can trust the information that you measure. And that all the biomass processors are really up to the state of the art. You have a website here. You have quite some information on this website. I will go through that. It's work in progress. It's quite new. We are still involving it. You can see the description of what's happening. The release note, every version of the processor which is delivered, you have all the documentation which is available there. Very soon there will be linked to the configuration in case you want to reproduce all the configuration. Input data, you have linked to quality disclaimer, which is all the anomalies that we encounter on our data. This is also work in progress. We'll put all the anomalies that you have for egg formation, also which is related to the FAQ, where we describe here main question that we have all the time, how the acquisition are working, what are these strange things that I see on my images that are usually radio frequency interferences from other sensors, from other system, linked to different elements and linked to something that we call BioPal that I was talking about before, which is the open source project. So here we explain if you want to contribute to BioPal, how to do, from just opening a ticket because you found a bug in the software, an issue with the data, to being part of the development of the project. How to file a report, how to report. This is also work in progress. The first time we do that for a space mission, so it's completely new to us. And here you will find all the information which is needed to contribute to the project. And you have a code of conduct. You see everything to understand how to work together. Here you have Git. You must be familiar with Git, GitHub. We put on Git all the source code of the processor. Every big updates that will be released will be published there. Here you will have the possibility to contribute, but also, for example, to copy with Git the source code. Then to go on the platform. This is the map platform that I was showing before. You have different elements in this map platform to help you to explore the data from visualization analytics. Processing is just processing on demand. You pick a processor, you change some parameter, you pick the area, you generate data. And here a Jupyter Lab that allows you to modify the code. You can install additional library, update them, and you can do a Git clone, for example. So the Git clone will connect to Git and get the source code you need. The idea here is to allow you to get any version of the BPS here that you can compile, and you can run the processor of the biomass mission. It can be useful for studies, also for students. You have all the internal resources, so additional files that are directly already mounted and located in your workspace if you need them. And you have a direct access to all the biomass data. With some example, how to query the catalog with an API that you can use also from your computer. I was saying before, you can query the catalog to get over an area, a particular data information, query the data with some condition from the metadata, and download all the data you need to run it. So what we are working on, this is a little bit preview, is also validation. So to have a Jupyter notebook, so using the open in situ data and some open validation methods to allow you, given, I don't know, an AGBD map for a state or for a disturbance map that you would have generated, to validate this map. So helping you to plot the map and to connect to the in situ data to derive some statistics. The idea is that everybody should use the same methods, same metrics, and same in situ data to be able to compare the results that we all obtain. Here, this is just an example that was made for airborne campaign data. You see comparing the estimated biomass from a given AGBD map the plot measured during the in situ campaign, and here you compare the different results. The idea is to start with the first definition implementation of the algorithm. Anybody have the possibility to modify the source code locally to generate the corresponding data set, to validate it himself or herself, because you have access to the validation in situ data. If it's an improvement, it's better than the ISA product, propose it as an improvement, make a pull request as a contribution, and it will go through the verification approval, and it could become the new baseline of the mission. So the idea is to arrive faster to stable algorithm for the mission in a cooperative approach, and anybody, also people outside of the core science team, can contribute to the product improvement cycle. For the space mission, usually nobody outside of the core science team can get access to the source code or contribute to it. And here, for the first time, we try to open it. And it's well adapted to innovative R&D mission like BIOMASS. Here, I will finish with a few examples of BIOMASS images and products to show something a little bit nice. You can see here a Bolivian forest and a river. What is quite interesting is that the color, of course, look green, but it's because it's different polarization that are combined in a red, green, blue channel to look with the forest a little bit green. But these are kind of fake colors. And you can see here that you see the flooded river, the flooded area of the forest around the river, which is not visible with all the type of sensor. You can see the topography inside the river. You can see this little river network. So it's really quite impressive. Here you have a comparison of northern Brazil between Sentinel-1, where you have almost no penetration, BIOMASS, where you're really sensitive to the different elements, and Sentinel-2 Landsat, where everything basically looks almost green, because you have just information on the surface top of the forest and not on all these details that you can see here. We have incredibly beautiful images also of not only of a forest, but also here you see volcanoes. It's quite well adapted to monitor all the changes as are in general on topography. Here you can see volcanoes. We have also some texture, as you can see, over the sea. This is also something that was a little bit unexpected. We have very beautiful sea pictures. Here you have again a comparison between Sentinel-1, Sentinel-2, and BIOMASS. Also a mountainous area of a desert, and you have a penetration. You can see a lot of details here because you have a big penetration with BIOMASS data. Over ice on glacier also we have penetration in the snow, and we have incredibly a nice color, strange color that we still we need years to interpret and understand. We have a very preliminary level 2 product that we generated a little bit by hand, and we're trying to transpose that to something more automatic here, a forest height map that you can see on north of Brazil and Suriname, which is very promising. We're still validating it. And here a first tomogram, so in 3 dimensions, you can see the vertical level of the forest. So it works very well as expected. And we are also improving it and understand how to bring that for the longer term. So the kind of summary conclusion, the BIOMASS mission was proposed in 2005. The implementation started in 2015 and the satellite was launched in 2025. The first images processed are extremely promising and showing great potential. The data is available, open and free to the general public if you are interested. It's the first P-band SAR and first systematic radar tomographic space mission. It's a true Earth explorer, as we call it at ESA, so there are a lot of unknowns, exciting science and global biomass mapping. And this new unique vision of Earth from biomass would extend beyond the forest and into the measurement of ice, subsurface geomorphology in desert, topography, ionosphere, ocean. And it's finally the first open source Earth Explorer with open algorithm, open in situ data, and open cloud computing platform. Thank you for your attention. Do you have any question?
Oh, okay. Here we have the microphone. Thank you very much, Clément. It was quite an impressive work and perfect timing, by the way. Thank you very much. So we have time for a few questions. Francisco, of course. Here's the microphone for you.
Thank you, Clement, for your talk. Can you hear me?
Yes, I can hear well.
Okay. So I have two questions related to the interferometric capabilities of the mission. When you look at how the mission was designed, it looks a lot like NISAR from NASA. So for a moment, I thought it would use a digital beamforming technique instead of a strip map. So I was wondering, why was it built like that instead of using like a planar radar antenna like that of Sentinel or Envisat?
Because even NISA doesn't have a planetary antenna. We have a planetary antenna we have for Roselle, and at L-band, it's very challenging. And the problem of antennas is that the lower the frequency, the bigger the antenna needs to be. At P-band, the antenna would have been enormous.
Okay, I understand.
NISA, it's a little bit easier. They are at L-band. ALOS is using a planar antenna. It works well. But already they made a choice to have a reflector because there are pros and cons using planar antenna versus a reflector. Everything is a question of compromise. For BIOMASS at P-band, planar antenna would have been too big, too heavy.
Okay,
for space. It's a lot of power also you need to transmit. So the best in terms of compromise technically was to have you have 4 small antennas and a 12-meter reflector.
Okay.
In terms of acquisition mode, we have only strip map. Not ScanSAR, not different type of exotic methods. Already P-band was complicated in terms of instrument.
Okay, thanks. And the second question is, it's P-band, so it's 70 centimeters long. So there are certain processes on the solid Earth, for example, glacier motion or large eruptions that can be studied using two-pass interferometry at P-band. So I was wondering if the mission actually has the capability to make a P-band interferogram like that that would be equivalent to a C-band interferogram from Sentinel. That was not clear to me.
Of course. Of course. This is what we do. So the orbits are particular. The orbits are optimized for tropical forest, for the equator, for example. So for Antarctica, currently, we don't have good orbits to do interferometry. But during the commissioning phase, we're having orbits that were optimized in a different way. So without these different observation angles that were allowing to have baselines of Antarctica. So we acquired a big data set of data over the Antarctica that allows to do interferometric techniques. And we derive the coherence. I mean, we do that. We do that of Antarctica. Antarctica is a little bit secondary objective, so it's a little bit less priority. But of course, we do interferogram. You can do them of a mountain, and the orbits are good when you are around the equator, the 2/3. When you go below 60 degrees, it's quite fine. It works very well. You can do tomography. It's derived for tomography. So you have really 7 bands that are 15% of the critical baseline. So to reach with the 7 past 90% of the critical baseline during the tomographic phase. And during the interferometric phase, between 2 passes, you will have 30% of the critical baseline. The idea is that in case 1 pass is missed, you can add another one and you are still within this 90% of critical baseline. So really the orbits are made to do interferometry. You take 2 techniques and the level 1C are stacked. They're co-registrated data. So they're ready to be used for interferometry.
Great. Thank you very much.
Thank you very much. We have a question from the chat. Veronica?
Thank you. Leonardo asks, why did you use Python instead of R?
So we use C and Python for the level 1, then only Python for the level 2, level 3, because for the scientists, it was a compromise. It was something that was easier, let's say, to program, to optimize. We use R for the validation, so for the in-situ measurement, because the forester, they use a lot of statistics and they're usually using R. In terms of SAR processing, R was not fast enough. There was not enough library. In Python, you have a lot of library to parallelize things. optimize a thing. If you go for Dask programming, for example, it looked more mature, more optimized to do SAR processing. But we use R for validation. And the tools for validation are coded in R. We are still working on them. They're not yet released, but they will be released in BioPal quite soon. And the map platform is supporting R and Python and Julia, Rust, all the open codes, open languages.
Yeah, actually, the the interaction platform is quite impressive. Thank you very much. A lot of hard work in there and a lot of contribution to the work of scientific work and professional work around the world. I have a curious question. Let's see, if I understood well, in order to cover the planet, you have to jump between different orbits. That means that you are spending energy to jump between orbits. How does that impact into the lifetime of the mission?
So the mission was planned for 5 years.
Okay.
But we are quite happy because first, the orbit injection was very good. You always plan a margin to put the satellite in a good orbit. Sentinel-1A, for example, was 10 kilometers too low, so spent months to put it in a good orbit. BIOMASS was in a very good orbit, so we made some economy of fuel. And we realized that also maintaining the orbit and avoiding objects was not consuming that much. We always planned a lot of margin with space missions, so we could last 10, maybe 15 years with the current configuration. What could happen is that we could decide to change the approach we have today, so doing interferometric configuration until the end, and redo a tomographic configuration, or do a different standard strip map that just continuously cover the globe if we see that interferometric acquisition are not bringing anything. It's an Earth Explorer. We have something planned already today, but it could be changed if we realize that a better configuration could be explored.
That's very good news anyway, that it's going to last for 15 years. That's 3 times.
Let's see 15 years, but currently
Well,
it seems at least 10 years should be fully supported.
We have another question from the chat. Leonardo asks, what challenges in the traditional limitations of SAR images did you encounter using P bands, such as speckle noise, etc.?
The issues we have are not so much to speckled noise, because we have quite a good instrument, which is a little bit, the noise floor is lower than what we're expecting, than the requirements. So the industry did a very good job there. It's problems that we were expecting that are related to mainly ionosphere and radio frequency interferences. So we're expecting that because we are at a lower frequency, so we are more sensitive to the ionosphere. The atmosphere is charged electrically. So if you know this representation of electromagnetic field, it goes close to the pole, you have this aurora borealis, but still it's charged electromagnetically. Now we are in the peak of the solar activity, so we have an atmosphere which is quite charged, and we see some artifacts appearing on our images. And when we do interferometry, even on strip maps, sometimes we see stripes that are coming from the ionosphere. And we have correction for that. The first test of the correction, they were not working fully as we were expecting, so now we're trying to tune them. We're considering one homogeneous ionosphere vertically. It doesn't seem to be the case, so now we're configuring one with different layers. We still need to tune the different layers. The ionosphere is the first big difficulty. The second one is the radio frequency interferences. This is something we have with all the SAR missions. There are people emitting, or objects, communication, military system emitting in the same frequency. And as you could see, the satellite is very sensitive to the backscatter, which is measured. So it's impacting the images. We have corrections that are irritated from Sentinel-1. And the problem is that Sentinel-1, the frequency band is larger. Here it's 6 megahertz. It's quite small. So we are much more impacted, and our corrections are not always working. So we have a lot of data with issues, so short term, and we realize our correction also sometimes was overreacting and degrading the data. So when we were doing interferometry, it was degrading the interferometric estimation. and the biophysical estimations. So we turned off on some areas of the world, South America, South of Africa, and we turned it on other areas where there was a lot of RFI. So in Asia, Middle East, North of Africa, and more, let's say, North of Asia. But this is something we're still working on. Now we're investigating a new approach. Let's see if it will work as well as we want. We are not happy today of what we have, but we started distributing the data with some big label that you will encounter this issue. And we hope that in next month we'll solve most of these issues.
Perfect. Thank you very much. Are there any other questions or comments? No? Well, thank you very much. Merci beaucoup, Clément. It was a great presentation.
Thank you very
Lots
much.
of good information. And thank you also for all the data that we're going to be digesting soon, I hope. Thank you very
Thank
much.
you very much for the invitation. I will share my slides so you can use them, go
Please
through
do.
them
Please
later
do.
on.
Thank you very much. Oh, the video is also going to be published
Have a
in
nice
our
day.
YouTube channel. Thank you very much. Goodbye. Enjoy your
Bye-bye.
Friday.